Welcome to part 2 of this lab rat introduction video. I'll start by describing in more detail the experiment we are going to build. This will be a simple stimulate and acquire experiment to demonstrate the amazing capabilities of lab rat and the Synapse software. In our experiment, we will use the audio stim gizmo to play a short tone burst from the lab rat speaker. You, as the subject, will clench your fist when you hear the tone. We will use your EMG signal burst and the timer gizmo to measure the latency of your response. There are some parasitic delays associated with the lab rat interface and the sound travel time from the speaker to your ears. But for our purposes here, we will keep it simple and ignore these factors. So let's add the needed gizmos to our experiment. First we'll add the audio stim gizmo. Click on the RZ2 in the processing tree, and expand the stimulation category of the gizmo picker. Drag the audio stim gizmo onto the RZ2 and drop it. I'll move Corpus out of our way by clicking the minimize button. Here is the audio stim configuration dialog. The audio stim gizmo can generate all sorts of fancy stimulation patterns. In this demo, we'll use its pulsing feature, with a jitter applied, to get multiple stim pulses, with random onset timing. There are lots of options here, but for our purposes, we can ignore most of them. We do need to set up the parameters for our signal, so click on the Parameters tab. Parameters are a powerful signal control feature of Synapse. I'll forego the details in this demonstration, but I recommend you watch the informative two-part video on parameters. It's available on our website. For our purposes here, I'll just set the needed values as constants. Let's do 5 pulses, with an average presentation interval of 5 seconds, and a 50% jitter. A short pulse of 100 milliseconds should work for duration, and I'll set a nice middle A note for the tone frequency. We're almost done. Click the third Options tab and set the minimum system sample rate to 12 kHz, and select the option to save our stim signal continuously, so it will appear in the scrolling plot at runtime. Click the Commit button to save our changes, and we are ready to add the last needed gizmo to our experiment. I just remembered, I forgot to set something on our neural processor gizmo. Click the I/O detail button to see a simplified gizmo function diagram, complete with its active inputs and outputs. Note, the gizmo output from our filter is currently turned off. But I can enable it here, on the Filtering Options tab. When I press Commit, the experiment updates, and you'll see the gizmo output is now turned on. Let's hide this diagram by clicking the I/O button again. The last gizmo we need in our experiment is the timer gizmo. We'll use it to time how long it takes you to respond when you hear the tone pip. We need to connect it to both the audio stim gizmo and the neural processing gizmo, so we can time the onset delay between these two signals. Click on the audio stim gizmo in the processing tree, and then expand the logic category in the gizmo chooser. Drag the timer gizmo onto the audio stim gizmo. Verify the correct signal from the audio stim gizmo is connected to the timer's primary input, and dismiss this dialog. Now select the time between measurement option, and the milliseconds units option. When I commit these changes, the dialog will reset, and a second input will be enabled on the timer gizmo. I'll toggle on the gizmo I/O diagram, so you can see this change as I press the Commit button. Now, I'll just select our neural processor output as the second input signal here, and our timer will be configured to time the difference between the audio stim and neural processor gizmo outputs. We will use the timer's bounding feature to define the allowed response window. Click here to enable the feature and enter 100 milliseconds as the minimum response time. We can leave 1 second for our maximum time. Now click Commit to accept these changes and press the Inputs tab. Here we can set up the needed thresholding to detect our signal onsets. For input 1, we just need to detect any voltage that departs from 0, as the audio signal gates on. I'll set this threshold to 1/10 of a volt, as our default. You may recall, from part 1 of this video, that the neural signal detection threshold we estimated to be about 50 microvolts. So let's set up input 1, to scale our signal to microvolts, and set the default threshold to 50. Now, click on the Miscellaneous tab. The last thing I'll do, is turn on the runtime interface, so we can tweak our thresholds, and see our results in real time. Commit these latest changes, and let's see if all is connected, as we intend. Click this little puzzle piece button, and a diagram, showing how our gizmos are connected, is displayed. Everything looks good here. The EMG signal from the lab rat amp flows through the neural processor and then to the second input of the timer. The output from the audio stimulator goes to the first input of the timer. Oops, I just realized, we won't be able to hear our tone pip signal, because we have not connected it to the DAC output and speaker. So let's do that now. I'll position the diagram window out of our way, but keep it visible, so we can refer to it as I make the changes. Looking at the LabRat dialog, we see a tab labeled Other I/O. There's information on this page about how to connect the DAC to our audio stim signal. You may recall in part 1 of this video, that I said the LabRat is connected to Synapse, through Corpus, and the emulated RZ2. This means, the general I/O for LabRat is accessed through the RZ2, just as it would, if we were working with a full-size TDT system. These buttons will jump us to the right place in the RZ2 dialog to set up these I/O. So click the DAC button. Now, we'll turn on DAC 9 for single-channel operation, and connect it to the output signal, from the audio stim gizmo. When I click the Commit button, the experiment will be updated, and the connections diagram reflects our changes. We can see, the audio stim signal now flows to both the timer's primary input, and the DAC 1 output, which is connected to the LabRat's built-in speaker. With that fix in place, we're ready to run our experiment. Let's do a little housekeeping, before we switch into record mode to run our experiment. First, let's save our experiment into the Synapse database. Once named, Synapse will automatically save your experiment each time you make an edit. A revision history will be maintained, and you can peruse and revert changes as needed. I'm entering some sample notes and selecting an icon for my experiment, so I can easily identify it later. When I click Save, you'll see the changes reflected here. Before you can go into full record mode, Synapse requires that you select a subject, so let's do that now. I'll create a new subject here. As with the experiment, you can enter notes, and select an icon. Click Save, to add me to the database, and select me as the current subject. Notice that with everything properly set, the record button is now enabled. Although, for our purposes here, we will use Preview, meaning the data will only be temporarily saved to the hard disk. I know the anticipation must be killing you. So let's switch into preview mode, and verify all is working as we expect. The EMG trace is still active and properly scaled. But I need to scale the audio stim trace into a reasonable range, which will be about 1 volt. Press Shift and drag upward, as we did before. This bottom trace will show a marker each time a response is measured and recorded. I'm going to switch the short bar option off, so we will see a long vertical line for each value recorded. Now, I'll drag the windows around and position them to suit my needs. I like to keep my control windows organized to the left. Right-click, and choose a split option, to unstack tabbed windows, as I'm doing here. Windows can be positioned any way you like, and the setup will be saved in the database and reloaded next time you run this experiment. I'm almost done, then we can fire off the audio stimulator and run the test. Click the strobe button to start a sim sequence. The first pulse comes right away, but the following 4 will play randomly. Clench your fist each time you hear the stimulus. You may need to adjust the level knob on the lab rat box, so you can hear the signal. In this plot we see the stimulus signal followed by my response signal. The blue line shows where my response was recorded, and the yellow number down here reports my latency time in milliseconds. Notice my latencies are being measured at about 225 milliseconds. Are you showing something similar? 5 pulses play each time you press the strobe button. To run again, simply press the strobe button again. All of the data you see here, including the measured response, is being saved to the computer's hard drive. You can access this data in a variety of ways, including using APIs written for MATLAB and Python. You can even access the data in real time while we're recording. Remember, we're in preview mode, so our data is not being saved permanently, and will be overwritten by the next preview session. Use the record button to run a record session, and save the data for later access and analysis. I hope you found this demonstration useful and informative. It should give you a small glimpse into the power and performance of LabRat and the Synapse software. Remember, there are numerous instructional videos on the TDT website and I encourage you to check them out. Goodbye for now and good luck with your LabRat system.